Dr. Shankaraiah from Department of Physics. In the last presentation, I have discussed about introduction to crystal structure. So in this, we have discussed the various concepts, for example, classification of solids and types of crystals based on the bond between the neighboring atoms and so on and so forth. So today I am going to discuss about space lattice, basis, unit cell and lattice parameter. So in today's presentation, I will discuss about next topics in crystal structures: space lattice, basis, unit cell and lattice parameter. So what is the space lattice? Irregular and periodic arrangement of atoms is the most important feature of crystals. The actual arrangement of atoms is called the crystal structures. We know that crystal is nothing but the regular periodic arrangement of atoms, right? So that we have discussed. And how do we find out that whether crystal is having regular periodic arrangement of atoms or not? Then we can use X-ray diffraction. Using X-ray diffraction, we can look at the crystal structure. The crystal X-ray diffraction will give different results. If it has a crystal structure, you will get different X-ray diffraction. If it is amorphous solid, you will have a different crystal X-ray diffraction. So X-ray diffraction is an experimental technique that can be used to look at the arrangement of atom or crystal structure of a solid. So here the actual arrangement of atoms is called structure. So here in this picture you can see a sequence of periodically spaced points. Okay. So you have a lattice point, you have an atom here, you have an atom here. So there are different atoms, for example, and the separation between these two atoms, any of these atoms is T1. So that is why we are saying equally spaced, periodically spaced points. So the distance between any 2 points is same. Okay. So that is also called as period. So that period, the distance between 2 points is called T1. So these points are periodically spaced points. Right? So suppose the atoms or clusters of atoms in a crystal are represented by points that correspond to their mean positions. Okay, so I have an atom here, I have an atom here, I have an atom here, I have an atom here. Okay, so now I am going to represent the mean position of this atom by a point. The mean position of this atom is represented by a point. The mean position of this atom is also represented by a point. The mean position of this atom is also represented by a point. Okay, so I'm supposing that the mean position of each atom is represented by a point that corresponding to the mean position of atoms. Then we obtain a regular distribution of points in space. These points are called lattice points or lattice sites. Okay. So now I have for example, I have a solid, and in solid contain many atoms, and for example, these are the atoms and these solids. Okay. So now I'm going to represent the mean position of this atom by a lattice point, the mean position of this atom by a lattice point, mean position of this atom by a point, and mean position of this atom is also point. Okay. So the points that are representing the mean position of atoms is called lattice point. Okay. And are lattice sites. So when we represent these mean position of atoms by a lattice point or lattice site, we are going to get a regular distribution of points in space, right? So you can clearly see there is a regular distribution of points. The three-dimensional network of regularly arranged points in space is known as space lattice. Okay. So what is a space lattice? Space lattice is a three-dimensional network of regularly arranged points. Three-dimensional network. So I can draw only 2 dimensions here, right? So of course I can draw 3 dimensions also, but that is a bit difficult to visualize. So a 3-dimension, if you are able to draw the 3 dimensions, so the space lattice is nothing but 3-dimensional network. Okay. So this is one network along one direction, this is another network along another direction. So if you keep on drawing this lattice points which represent the mean position of the atoms, so you have networks. Okay. So these two are the networks in 3D. If you have another dimension, so in Z direction, if I plot like this, okay, so I have, okay, so I can have a 3-dimensional network of regularly arranged points. Why am I saying regularly arranged points? The distance between any 2 points is same. the distance between any two of these lattice points is same. That is the reason why I am saying these are regularly or periodically arranged points, and such a network in 3 dimensions is called as space lattice. What is this? These the points that are representing the mean position of atoms. Those are called lattice points, and the network that is obtained by placing these lattice points at the mean position of each atom, we are going to get a three-dimensional network of such a regularly arranged points, and such a three-dimensional network is known as space lattice. So a point is a dimensionless and shapeless entity. Therefore, a lattice is merely an imaginary geometrical network. So we are saying here that space lattice. So what do you mean by a lattice? Right? A lattice is a merely an imaginary geometrical framework. We have to imagine this as a framework. Lattice, we have to imagine this as a geometrical framework, right? So because we are representing the mean position of each atom by a point, and the distance between any 2 points is same, and that is why we are saying that these points are periodically arranged points in space. And when we when we represent these atoms, mean position of atoms by these points, we are going to get a network in 3 dimensions, right? So such a network we have to imagine. So lattice is an imaginary concept, right? So because we are representing the mean position of atoms by a point, and those points are called lattice points, and we are going to get a network in 3 dimensions, and such a network in 3 dimensions where you have regular arrangement of these points is called space lattice. Okay, so a space lattice is defined as an array of points in 3 dimensions in which every point has surroundings identical to that every other point. So the definition of space lattice is given here. A space lattice is defined as an array of points. Okay, along x-axis, these are the points, so there is an array of points. Similarly, if I consider this as y-axis, even along y-axis also there is an array of points. Okay, so a space lattice is an array of points in 3 dimensions, not only x, y, but also in z direction. So in 3 dimensions, you are going to get an array of points in 3 dimensions in which every point has identical surrounding. Okay, here this has same surrounding. If you go to this point, this also has same surrounding. If you go to this point, this also has same surrounding. Okay, so space lattice is defined as an array of points in 3 dimensions in which every lattice point has the same surrounding identical to that of every other point. Such a geometrical framework is called as space lattice. Okay, but how are we going to generate such a space lattice? Space lattice can be generated by successive translations of an initial point. Starting from a initial point, you can generate this space lattice by successive translations. So you are going to use the translations. By using these translations, we are going to generate this space lattice. We will see how we are going to generate this space lattice using these translations in 3 dimensions, because we have defined space lattice as a 3 dimensional array of points in which every point has the same neighborhood compared to any other point. So all the lattice points have the same neighborhood, and such a network of or array of points in 3 dimensions is called as space lattice. And we are going to generate this space lattice using translations starting from an initial point. So a very simple operation of repetition consists of repeating the unit without change after translating it a distance t. Okay, so repeated applications of translation of a given length and direction, for example, of some length t1 to an initial point generates a sequence of periodically spaced points or row of points. Okay, so I'm saying that I'm going to start from an initial point here. So this is my initial point R, and then I'm going to translate this point at a distance t1. So when I translate at a distance t1, I'm going to get the point at this r plus t1, right? So now again repeated application of translation. So I'm going to apply this translation repeated, right, using the same length. Now if I again translate this point at a distance t1, again this t1, so now I'm going to get the point at this which is having r plus 2t1. Again, if I use the translation, I'm going to get the point here, the same distance, I'm going to get the at a distance of r plus 3t1. So by using this repeated application of translation, I'm going to generate a row of points in one direction, right? So these are all periodically spaced points. Now, the repeated application of some other translation, which is not along the same line above to the above row of generates a planar array of points. Now, so this I have generated a row of points or periodically spaced points in one direction. So so I have generated a row of points. Now I am going to apply this translation again in another direction. Starting from an initial point here, I am going to translate this point at some other distance. You can take the same distance or some other distance. So if I translate this point at a distance t1, I am going to generate a point here at a distance of r plus t1. So again, I can translate this point. So again, at a same distance t1, I am going to generate the point at a distance of r plus t2. So repeated application of this translation, we are going to generate now a plane of points, right? So now at this point, so starting from this point, again, if I apply the translation of the same length, I'm going to generate now a plane. Okay, so I'm applying this translation to all the points, right? So now I've generated a plane. If I keep on drawing, I will generate a plane or two-dimensional array of points. So initially I've started the translation at a point R, and I've generated a row of points, periodically spaced points or a row of points. Then I have applied the translation to each of these points, row of points, and then I have generated a plane. Okay, planar array of points. So basically, I have generated a plane in two-dimensional array of points, applying repetition in two directions. Right. So now I am going to again apply this repetition translation, a third translation, not in the same plane. Right. So in other plane, in the same plane. So in the beginning, we have started from an initial point and we have generated row of points. So I've applied this translation not along the same line, in another line. So this is how I have generated the row of points, and then I have applied the translation in another line. So I've generated the translation in another line. So that is how I've generated the plane of points or planar array of points, two-dimensional array of points. Now I am going to apply this translation again, not in the same plane. Okay, so basically I have this I've generated first a row of points, right? So then I have generated another, I've applied this. So this is the first row of points I've generated, and then I've applied the translation in another direction. So I've generated a plane, right? So this is how I have generated a plane. Second, when I applied the translation second in the another direction second time, now I am going to apply the translation in another plane, not in the same plane but another plane. So if I apply the translation another plane with the same distance, so I am going to generate a three-dimensional network of points, right? So I am going to apply this translation another plane. So then okay, so if you keep on doing this, then we will be able to generate a three-dimensional network of points. Okay, so yeah, so a third translation not in the same plane applied to a two-dimensional lattice generates a three-dimensional array of points is called a space lattice or simply lattice, right? So you can clearly see when I applied the translation in the other direction, not in the same plane, then I am generating a cubic lattice. Basically, I am able to generate cubes. At every point, I am able to generate cubes, right? So you can generate a three-dimensional structure by applying translation along other direction, third direction. Okay. So when we applied the translation starting from a point R, when I applied the translation repeatedly, I have generated a row of points, and then I applied the this translation not in the same line but in the other line. Then I have generated a planar array of points. Then third time I applied the translation not in the same plane but in another plane. Then I have generated a three-dimensional network of points, and then this is called as space lattice or simply lattice. Thus, lattice points satisfy the condition of periodicity. Condition of periodicity. If you look at any, go to any, take this point and look at its neighborhood. Okay, take any other points, you will find the same neighborhood. Okay, so these all those points are going to satisfy the condition of periodicity. Okay, so that we have discussed yesterday. Hence, the crystal structure, that is the arrangement of atoms in the crystal, cannot be understood with reference to can be understood with reference to a lattice. So, to understand the crystal structure, we need to know the lattice. Without having a lattice, it is very difficult to understand the crystal structure, because we are going to represent the mean position of atom by a point, and that is how we generate a lattice, and that is how we are going to understand this crystal structure. Okay, so now we have defined what is this space lattice and or what is a lattice, and how do we generate the lattice. How can we generate the lattice? Using translation. So that is what we have discussed. So the space lattice is the skeleton upon which crystal structure is built by placing atoms are near the lattice point. So how did we build this space lattice? Space lattice is the skeleton upon which crystal structure is built by placing atoms on lattice points. Okay, so you can imagine that you are going to represent the mean position of atoms by a point, and then you are going to generate the lattice, and these lattice points are nothing but the atoms. That is how you are going to generate this space lattice. So study of crystal structure becomes simpler when it is represented by a space lattice. If we represent these atoms of a solid or a material by this lattice, it will be very easier or simpler to understand the crystal structure. So you can see this first a row of points are generated, and then a planar array of points generated using this repeated application of translation. Right. So then you can apply in third dimension, right? So not in the same plane but in another plane. When you apply the translation third time, you are going to generate this space lattice in 3 dimensions. So space lattice is a 3-dimensional network of points where all these lattice points are arranged on regular periodic manner. So that is about what is a space lattice and how do we generate a space lattice. Now, what is a basis? So a space lattice is a mathematical abstraction, right? So this is all you have to imagine. This is a geometrical framework. Space lattice is a geometrical framework. That means that we have represented the mean position of atom by a lattice point, and we have repeated the translation or by representing the lattice point, representing the mean position of atoms by a lattice point. We have generated a network of points, and those network of points we have defined it as a space lattice. So it is totally a mathematical abstraction. Space lattice is a mathematical abstraction. The crystal structure is formed only when a group of atoms is identically attached to each lattice point. Okay, so we have just generated a network of points, and we have defined that network of points in 3 dimensions. Those points are regularly arranged, right? So the network of points in 3 dimensions where all the lattice points are regularly arranged is called as a space lattice. Now we are going to attach, okay, we are going to attach each lattice point atom, a group of atom or a single atom. You can attach a single atom or a group of atoms identically to each lattice point. So that will give us actually the crystal structure. Okay, so the crystal structure is formed only when a group of atoms or atom is identically attached to each lattice point. So we will see that in the figure. So you can see this, right? So each lattice point is attached. This is attached by an atom. This is attached. If you want to generate a NaCl crystal, for example, sodium chloride crystal. So each lattice point you can have Na sodium plus chlorine, sodium plus chlorine. So when you represent these lattice points by these sodium and chlorine atom. So you are going to generate a sodium chloride crystal, right? So the atoms are a group of atoms that we are going to attach to each lattice point is called as a basis. What is a basis? The group of atoms are a group of a single atom or a group of atoms that is associated with each lattice point. That is what is called a basis. So the basis must be identical in composition, arrangement and orientation such that the crystal appears exactly the same at one point as it does at other equivalent point. Okay, so we are going to attach a group of atoms or a single atom to each lattice point, and the group of atoms are a single atom that is attached to each lattice point is called a basis, and the basis must be identical in composition. It is identical in composition, arrangement and orientation such that crystal appears exactly same at everywhere. So crystal appears exactly same throughout the structure, right? So a crystal structure is thus the result of two quantities, namely a lattice and a basis, right? So first we have generated a space lattice by using translation repeatedly in 3 dimensions, right? So once we generated the space lattice, we have attached a single atom or a group of atoms to each lattice point. Okay, and that is called as basis. Basis is nothing but the atom or a group of atoms that is attached to each lattice point, that is called basis. Okay, now we have generated lattice and we have attached a group of atoms to each lattice point. So lattice plus basis, this will give us the crystal structure. So that is what I have discussed here. Okay, if this is a lattice, so we have generated lattice using translation, and then we have attached a basis. Okay, so this is a lattice. So this is lattice and this is basis. Basis is a single atom or a group of atoms. Okay, so lattice plus basis, you are going to get a crystal structure. For example, NaCl, I am going to attach Na and sodium atoms and chlorine atoms to these lattice points. Okay, so for example, here these are the lattice points. So I can put sodium here, chlorine here, sodium here, chlorine here, sodium here, again here chlorine, sodium, like that. So by attaching these bases to each lattice point, I am going to generate the actual crystal structure that is required, right? So actual crystal structure is generated by using lattice plus basis. First you generate a space lattice and then attach a basis to each space lattice point. You are going to generate a crystal structure in 3 dimensions. So now we are going to discuss about unit cell. Okay, because of the inherent periodicity, the space lattice can be represented by a unit cell. Okay, so we have generated space lattice. We have attached group of atoms to each lattice point, and we have called it as a basis, right? And then we have generated a crystal structure using lattice plus basis. Now we are saying that because of the inherent periodicity, because if you look at the crystal structure, it is same everywhere, right? All the atoms are arranged in a with a same distance, right? So there is a regular periodic arrangement of atoms in a crystal, right? So because of this inherent periodicity of the crystal, the space lattice can be represented by a unit cell. Okay, you can use the unit cell concept because of the inherent periodicity of this crystal. Because in crystal, all the atoms are arranged in a regular periodic manner, you can define a concept called as unit cell. Okay, let us see. The unit cell is the smallest geometrical unit which, when repeated in space indefinitely, generates the space lattice. Hence, it is the smallest volume that carries full description of the entire lattice. So the smallest geometrical unit that you can define is called as the unit cell. And when you have a unit cell, repeat this unit cell in space. Repeat the unit cell in space, you are going to generate the actual crystal structure or space lattice. Okay, so that is what is a unit cell. Unit cell is the smallest geometrical unit which when repeated in space indefinitely generate the space lattice. And if you can define this unit cell for a given crystal structure or a lattice, you are going to get the complete description of the entire lattice. Okay, so that is unit cell. So for a unit cell, you can the lines drawn parallel to the lines of intersection of any three faces of the unit cell which do not lie in the same plane are called crystallographic axis. Right. So you draw lines parallel to the lines of intersection of any three faces of the unit cell. So this is my unit cell. So I have generated a unit cell for a crystal structure, and now draw lines parallel to the lines of intersection of any three faces, and you are going to get three crystallographic axes. Okay, I have three crystallographic axes, right? These three are the crystallographic axes, and I can define an angle between these two axes. Okay, between these two axes I have defined an angle beta, between these two axes I have defined angle alpha, and between these two axes I have defined an angle gamma. So this is A axis, I'm calling this as A, and this is B, and this is C. Okay, between B and C I have an angle alpha, between A and C I have an angle beta, between A and B I have an angle of gamma. Okay, once I define the unit cell, I am going to find out the crystallographic axis, and then I am going to define my angles, define the angles between any of these crystallographic axes of this unit cell. So the three translation vectors A, B, C lie along the crystallographic axis as shown in the figure. So three axes A, B, C. Okay, so these are the translation vectors, right? So we have discussed about translation. So each of these A, B, C are called as translation vectors. We have defined the unit cell as the smallest geometrical unit. When you repeat this unit indefinitely in space, you are going to generate the crystal structure, right? So this is the length of a translation, right? That is why we are calling this ABC as translation vectors. Now I have this unit cell. So when I repeat this again, I am going to generate another unit cell. So I have already C. So I have this as, this is my B and this is my A. So I can again draw this. Okay. So I can again draw this crystal structure. Okay, if you have any one more thing there, then you can draw this, right? So by repeating this unit cell indefinitely, you are going to generate the crystal structures. So the three translation vectors A, B, and C lie along the crystallographic axis that define the dimensions of the unit cell, and these are known as primitives. Primitives are nothing but the translation vectors along the crystallographic axis, and they are going to tell us the length. What is the length of this or the distance between two lattice points? Okay, so ABC will tell us the length or distance between 2 points along x, y, z directions, and these translation vectors are called as primitives. The angle gamma represents the angle between A and B axis, and the angle alpha represents the angle between B and C axis, and angle beta represents the angle between C and A axis. So the axial lengths ABC are called as translation vectors. They are also called as axial lengths along x-axis, along y-axis, and along z-axis. These axial lengths and the interaxial angles alpha, beta, and gamma. These two together are called as lattice parameters. So lattice parameters are both axial lengths ABC and interaxial angles alpha, beta, gamma. So these are called as lattice parameters. So lattice parameters are axial lengths as well as interaxial angles. Okay. So if this volume in space contains only one lattice point, we call it as a primitive unit cell. Okay. If unit cell, the total volume of the unit cell contains only one lattice point. We will discuss what is this one lattice point per unit cell. Okay, if the volume of the unit cell contains only one lattice point, then we are going to call that unit cell as primitive unit cell. Okay. See, if the volume of the unit cell contains more than one lattice point, for example, 2 or more lattice points per unit cell, then we are going to call that unit cell as non-primitive unit cell. Okay, most of the unit cells of various crystal structures contain 2 or more lattice points and are non-primitive unit cell. Okay, so we have defined primitives as the translation vectors ABC, and then we have defined lattice parameters, which are nothing but axial lengths ABC as well as interaxial angles alpha, beta, gamma. Okay. Once we define these lattice parameters, then we said that if the volume of this unit cell contains only one lattice point, then we are going to call that unit cell as primitive unit cell. If the volume of the unit cell contains more than one lattice point, then we are going to call that unit cell as non-primitive unit cell. So these are some of the examples of primitive and non-primitive unit cell. If the unit cell contains only one lattice point per unit cell, then it is a primitive unit cell. If it contains more than one lattice point, then it is going to call it as non-primitive unit cell. Okay. So these are some of the references which I've used in this presentation. To summarize this presentation, so first starting with, I have discussed what is a space lattice and how do we generate this space lattice using translation, and then I have also discussed about basis. Okay, space lattice is nothing but the three-dimensional network of points that are arranged regularly in space, and which is called space lattice, and we have generated this space lattice using the concept of translation that is applied repeatedly in 3 dimensions. First, we generate a row of points using the repeated translation, and then we apply the repeated translation along another line, which we generate a planar array of points. Then, when we apply the translation another plane, then we are going to generate 3-dimensional network of points that are arranged in a regular periodic manner, which is called as space lattice. Then we have discussed that basis. Basis is nothing but a single atom or a group of atoms that are attached to each lattice point. So combining space lattice plus and basis. So lattice plus basis will give us the crystal structure. Okay. So then we have discussed about unit cell. Because of the inherent periodicity of this lattice or crystal, you can define a smallest unit cell, smallest geometrical unit, which is called as unit cell. By repeating the smallest geometrical unit in space, you are going to generate the crystal structure. Okay. Once we find out the unit cell, you can define the axial length or translation vector. Okay. Once you define the translation vector, you can define the angles between these axial lengths, ABC, or the axial length or crystallographic axis. You can define the angles between these crystallographic axes, which are called as interaxial angles, alpha, beta, gamma. So combining axial lengths ABC and interaxial angles alpha, beta, gamma are called as lattice parameters. So then we have defined a primitive lattice which has only one lattice point for unit cell, non-primitive lattice which is going to have more than one lattice point per unit cell. Okay. So in the next presentation, I will discuss more topics on this crystal structures. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.